Hi, I'm Chen Liang from Zhejiang University. I'm happy to present our work here, which is published in ICCV'23. Semi-supervised learning differs from traditional supervised learning as it aims to maximize the utilization of unlabeled data to enhance the learning process. Previous approaches have often followed a pseudo-labeling pipeline. A teacher model provides initial predictions to supervise a student model. However, these predictions can be noisy, necessitating the use of a pseudo-label processor to filter out erroneous labels and improve the quality of pseudo-labels. One commonly used technique is the confidence thresholding, which filters out pixels with probabilities below a certain threshold. While in practice, this approach exhibits several problems. First is that it treats all categories equally without considering the hierarchical structure of labels, which is crucial in scenarios where label data is scarce. Second, the errors occur in the early training stages have no chance to be rectified in the subsequent learning. Third, it relies on empirically adjusting a threshold tau, which requires customization for each model and dataset, limiting the flexibility and generality of current methods. Lastly, as a data-driven approach, the filtering process also lacks interpretability. To overcome its limitations, we propose an integration of neural learning and symbolic reasoning. Our key insight is that symbolic knowledge can effectively resolve conflicts within predictions, or the so-called pseudo-labels, which may reveal model errors. For instance, we know that a pixel cannot simultaneously belong to both the cat and vehicle categories, but can belong to both cat and animal. Building upon this insight, we introduced Logic-induced to offer a principal method for modeling this process. Logic-induced consists of two steps, diagnose and sampling. In the diagnose step, we aim to identify and rectify conflicts in predictions. We leverage prior knowledge represented as a set of first-order logic rules, K. Each rule evaluates whether it is satisfied or not for a specific prediction. And then introduce a Boolean-valued pseudo-label O that determines whether a pixel belongs to a category or not. And we further define a normality identifier, a predicate T, that determines if a pseudo-label behaves normally without conflict. And we can now define that a conflict arises when the assumption that all outputs are normal is inconsistent with our symbolic knowledge K. And to explain the inconsistencies, a diagnosis is proposed by assuming that some outputs in a set omega are faulty. And now the problem has been reduced to a Boolean satisfiability problem, which can be efficiently solved in a greedy manner. This allows us to revise the pseudo-label to a logically consistent version, O'. However, there may be multiple consistent diagnoses, and determining the correct revision can be challenging. To address the problem, we modeled the likelihood of each diagnosis being correct using the multiplication rule. And to comprehensively estimate the probability of an output being normal, we consider both the predicted confidence and a degree of conflict. Intuitively, outputs violating established knowledge but having high predictive confidence are penalized more, indicated by a small value COS to increase the likelihood of correct diagnosis, and conversely, the high confidence indicates low probability of the abnormality, ensuring a balanced likelihood. To measure the degree of conflict, we employ the fuzzy logic. It provides a soft measure of how much a logic rule is satisfied, complementing the desired conflict degree. And we are now ready to estimate the likelihood of actual diagnosis and sample from this likelihood for the final one. Approach, as discussed above, is model agnostic and compatible with general knowledge described in first-order logic. And now we showcase its one specific application on structured video semantics that are commonly overlooked. We define three rules: composition, decomposition, and exclusion to form the logic-induced pipeline. Extensive experiments on the standard datasets demonstrated that the approach consistently outperforms the baselines. And we also quantitatively verified our K designs. And found some other interesting observations. More details can be found in our full paper. Here is the takeaways. Please contact me at our webpage if there requires any discussion, and thank you for your attention.